Hello, Panthera, and welcome to our new episode. Today I will derive the Oseen flow approximation. Oseen flow approximation is better approximation than Stokes approximation because it includes the inertial term of the fluid. Let us examine the problem and we will derive it very not so easily, but we will do it. So let's talk about first at the result of the flow. It tells us that if a ball is in the moving fluid with the velocity v infinity at infinity, far away from the sphere, then it creates for some values of the density and velocities of this fluid some these kind of vertices. It basically looks like a torus. It's a torus vertex behind the sphere, and let us introduce in the problem the Reynolds number. The Reynolds number is defined in this way. It's density of the fluid times v at infinity, the velocity of the fluid times the radius of the sphere divided by dynamical viscosity. So that is our Reynolds number is defined by this way. We can define it different way, but we will stick with this. And for a critical value of Reynolds number, the critical value is 8/5. The Stokes flow, which is basically coming from below to going around the sphere and then goes out, there is no vertices at all. But from this point, from critical Reynolds number 8/5, there is going to be two vertices, and also the fluid will separate at some angle. This angle is computed by this equation. Again, this equation holds only if when Reynolds number is greater than Reynolds number critical, which is 8/5. This picture is, for example, Reynolds number about I don't know, 10 or 20. Let's see. Again, there is also a point called we can call it far separation, or the length of the tail of vortices ends right here. This is the point when fluid separates, and the upper particle will go this in the up, and the lower will go to the sphere. So this point, it's basically distance z separation from the center of the sphere, and the z is exactly computed by this equation. Again, when Reynolds number is 8/5, this reduces to 0. Oh, I'm sorry, this reduces to 1, because it's gonna be like here there is no vertices, they are behind below this point. So let's start with talking about Oseen flow and its considerations, its equations we will be using. Firstly, I have to say that we will use again our equations like before. The first equation is the equation of conservation of mass, of the conservation equation. It is going to be like this: the divergence of velocity field is equal to 0. Again, we are assuming that the fluid is viscous and incompressible, so there is no rho with respect to, and also the fluid is stationary, not stationary. The field is stationary, so it means that it does not change in time, so this v is not function of time. Otherwise there will be another term, I think, or no, there wouldn't be. So the second equation I would tell you is momentum equation. It's basically Navier-Stokes equation, but the momentum equation balance tells us that the density of the fluid, this is density of the fluid, times acceleration mass times acceleration is equal to force, and it's the same case here in the fluid mechanics, force times divergence of the stress tensor. There is no force. We can assume there is a force due to the pressure in homogeneous gravitational field, but doesn't mind. We can add it later. And there is also this term, which in the last video we have neglected it, and because this term is basically material derivative, which is the derivative with respect to time, plus v dot gradient of v, the velocity. This term is basically zero because we assume the fluid velocity field is stationary. And this term we have neglected. Now we will not neglect it. The second thing is we will be using material equation or material constituent relation, which is this. It holds for Newtonians. We are assuming the fluid is Newtonian, so its stress tensor look like this. This is eta, the dynamical viscosity gradient of V plus gradient of V transposed, and I is a unit operator or unit matrix or identity matrix. I'm sorry, no unit matrix. So if we substitute in this expression to this one, we will get the Stokes equation. So the Stokes equation reads this: V rho times v dot gradient of v is equal to minus gradient of the pressure plus eta Laplace of v. We did it already before in the last video. This term is going to be neglected because of this condition. Then next, this equation is very hard to solve. This is basically Navier-Stokes equation, or in a stationary case, so the velocity field is not a function of time. And what Oseen really did or solved is the approximate equation which he was solving, and the condition, the assumption he made was that this term is gonna be because the fluid is basically all the time almost far away, so this term has to be always b infinity. This is the approximation times v. This is the real velocity field, and this is the approximation. We approximate the velocity field everywhere, this term, by v infinity. So the Oseen equation reads like this. So this is Oseen equation, and if this is linear equation because v infinity is constant. It's constant field. This is the equation we will be solving, or we will be not solving this equation but we will find approximate solution even to this equation. So what next? Again, v at infinity is this is Oseen equation. V at infinity looks like this, because v at infinity we will use polar and combination of polar and or cylindrical and spherical coordinates. This direction basically is the direction of z vector. So this is z vector. So this is going to be like this. V infinity is proportional to z vector, and the constant of proportionality is actually v infinity, the constant, the velocity at infinity. So if we substitute in here, we will get this equation, and if we divide it by eta, we will get rho times v infinity divided by eta. That's exactly a Reynolds number divided by a, and we will write for this, we will write gamma. Gamma will be will be our density times v infinity over eta. Otherwise, it would be confusing to write rho for cylindrical coordinates. So one coordinate from cylindrical coordinates. So the equation will be this one. It's gamma z hat dot gradient of v is equal to minus 1 over eta gradient of p plus Laplace of v. This is the equation. Now again, the trick is to look for or to search solution in this form. We will try this form of solution. What this form? This form. Let's say that the solution is going to be a curl of some vector field psi. This automatically solves this first equation, the equation of conservation of mass. So this is automatically solved, so we can use that. And again, as in previous video, from the symmetry arguments, we can show that this is only a function of phi vector field times psi, and the psi is a function of two variables in perpendicular in a plane where phi is constant. Again, we have our table here, so it's a function of two of these variables, z, r, rho, and theta. So that's our psi. We can something, or doesn't matter which two coordinates we will use. Next, again, if we substitute in this solution into this equation, which is basically this equation, we will get this. Let us first know that this operator is scalar operator, so it has no indices. Also, this operator is scalar operator. What does it mean? It means that you can switch this operator, which is vector, with this, because derivatives are switchable, yes, and this can also be switched because derivative of z vector is 0 because it's constant vector field. So this equation will read this. So this is going to be this. It's gamma z, and if we will substitute in this this gradient of psi is equal to we have to first I think I forgot something. No, I didn't forgot something. So this is going to be this, the pressure is here, so this is Laplacian of v and this, and we can switch orders of these operators as I tell you, and take curl of this equation, so there will be double curl of a curl, and there is going to be z, and there is psi vector field, and this is 0 because curl of a gradient is 0. So this is gonna be curl of Laplacian of psi. And again, we know that this operator is minus Laplacian. From our previous episodes, it's basically minus Laplacian because it's minus Laplacian plus gradient of divergence, and divergence of this is 0 because divergence of psi is 0. Why the divergence of psi is 0? Well, divergence of psi, it's divergence of psi phi, which is equal to, this is going to be gradient of phi dot product phi hat plus psi dot product phi, which is 0. This is 0. Why? Because our table tells us this is 0. This is 0 And this is also 0 because this is gradient, and gradient of function which has only variables r and theta, so this has to be some span of vectors r hat and theta hat, and they are perpendicular to phi, so this is also 0. So this equation is 0, so as this can be written as minus Laplacian. This is minus Laplacian. So now we are solving this particular equation. Again, we can switch the orders of this, no problem. So we will get this and cancel the minus signs because they are unnecessary here, and we will arrive to this equation, gamma z dot product gradient of Laplacian psi, it's equal to a Laplacian squared psi. This is equation we are going to solve now, and it's gonna be really hard or tough, and tougher exactly. First, I would remind you of some identities we have considered earlier, and these identities relates Laplacian with some special types and of 5 functions, which are functions of rho and some function of r, and vice versa, or something like that, for example. So firstly, let's write first we will denote with psi, with phi var of this letter. This letter should be this is gonna be like phi vector field, or the different phi. It's var phi or r, I don't know. Let's call it very phi. Or let's just not call it anyway, but this I will write for this letter, and this is the Laplacian, and we will compute Laplacian of this special form. So Laplacian of this, what's gonna look like what? Oh, this is not so hard, because Laplacian of two functions, it's some kind of we can use our tables from before, but there is a formula for Laplacian of two functions like this. Function in vector field is going to be Laplacian of the first, is basically Leibniz rule. Laplacian of the first times the vector field plus 2 times gradient of psi times gradient of phi plus psi Laplacian phi. And this is very easy to handle with, because this I will let as it is, times psi, and this is 0. Why? Because gradient of phi is proportional to phi times something, so the dot product, this is not proportional to phi, so this is 0. And the Laplacian of phi, we have to compute it before. Laplacian of phi, again, because the dot product with phi vector is 0, we can write it as a double curl with minus, and we know that the curl of phi is 1 over rho z hat. So this is Laplacian phi z hat minus 1 over not yet, phi curl of 1 over rho times z vector, and the gradient of z vector is 0 because it's constant field, so we have to only compute this part. So by Leibniz rule, it's minus 1 over rho squared times gradient of rho, which is rho hat, and rho hat cross z is rho hat cross z is minus phi. So this is minus and minus, so this is minus 1 over rho squared times phi hat. So this is going to be this is the same, minus 1 over rho squared phi, and I've put this after the bracket, so this is the term. So this equation is this, and I can add this to the blank page, so it will be we can use it later on. So this is the relation, so it's phi minus 1 over rho squared phi and psi phi hat. Next, the second thing I have to discuss with you is when the shape, the formula looks like this for psi. It's some function, it's rho times some function of r. We've considered it earlier, this shape or this particular case of the function. Then it's easy to compute this Laplacian of this vector field consists of phi times of psi times phi hat. It's very easy to do. I will do it. Basically, we know that this is gonna be this, so we have to only compute Laplacian of this part. So Laplacian of this part, Laplacian of rho r. This is very easy. We can use the same formula as before. So it's Laplacian of rho times r plus 2 times gradient of rho times gradient of r plus rho Laplacian of r, and this is what? This is gonna be Laplacian of rho, what it is. Again, I think this is going to be 1 over rho, but you can compute it yourself. Again, the this can be written as the gradient of the divergence of the gradient. This is rho hat, and the divergence of rho hat. Oh, that's very easy because divergence of rho hat is 1 over rho, so it's 1 over rho. 1 over rho times r, so this is 1 over rho times r, which is what? Which is just r, and then we will write plus, oh, this is rho hat times this derivative of r times rho hat, and rho, as there is not the formula, but I have to add it in, rho hat dot product with r is basically rho hat dot product with r is sine of this angle, because the cosine of this is sine of theta, and sine of theta is rho over r, so this is rho over r. The same holds for z, so this is gonna be z over r, so this formula will add in. So this is plus rho over r prime plus, and this is very easy to compute. This again, it's divergence of r, gradient of r is r prime times r hat, and this is going to be the gradient is r double prime times r hat dot with r, which is r double prime, plus the gradient, the divergence of r hat, which is 2 over r, so this is 2 over r prime. And if we put all together, we will get this equation. I will add it in. We will get this equation, the Laplacian of rho r phi is gonna be, again, we have done it before, but for reminder, to remind you, I've done it again. So it's gonna be what? There is this term will cancel with this term, because this is gonna be minus 1 over rho squared times rho r, which is 1 over rho times r, which is here. So this cancels out, so we are left with this rho times 2 plus 2 is 4, so this is the result of our compute. This is 4r over r times phi hat. So this is the formula we will use later. Again, you have seen it already in the video on the derivation of Stokes' law. The second equation, or I will use frequently, it's basically the same, but the special form of psi now it will be this one. We will be computing the Laplacian of z times rho times some function s of r times phi. Already we know what this looks like, because this is rho times, the Laplacian of this is rho times s double prime plus 4 over r times s prime, so we can use it later, or use it now. This is Laplacian of z times, again we use the Leibniz rule for the second derivative or for the Laplacian, so this is rho s phi plus 2 times z time dot product with rho s phi hat plus z times Laplacian of rho s phi. Well, this is not so hard to do, because Laplacian of z is 0, because it's a second derivative of z. You can imagine the Laplacian of Cartesian coordinates, where it's basically sum of the second derivatives, so this is 0. This is gonna be z hat, and the only term here, which is the gradient is going to operate on this and this and this respectively, because of Leibniz rule. When it operates on this, the term rho hat will pop up, and it will be killed by z, because they are perpendicular in coordinates. And the second thing which will be killed is this one, the gradient of phi. Why? Because again, gradient of phi is proportional to phi hat times another vector field. We don't care about it, and so it's also perpendicular to z, because they are perpendicular, so this is going to be 0. So only thing which will survive is this, the gradient applied on s, which is going to be s prime times r hat, and r hat dot z, we have seen it already, r hat dot z, it's z over r. So this is gonna be z time, this whole term is 2 times z over r times s prime. And this is also z and rho, and there is also rho and phi, which will survive because of the gradient does not care about this term, so they will go out. So this is gonna be, look, this is gonna be, I will write it to our table, because it's not so hard to put it all together. It's z times rho, it will survive. There is also second derivative from this term, plus 4 from the equation we have seen here on this row, and there are additional 2 of z prime, so this is plus 6 s prime over r phi hat. So this is the formula for this, and again, for a reminder, r and s are functions of r. So this is not needed. This is not needed now. I think it's enough for deriving this stuff. So let us focus on the actual derivation of the Stokes, the Oseen flow. So I would tell you that there is no solution which is exact to this problem, we cannot find it in any way. There is no way to find an exact solution. Maybe there is, but we don't need a super exact solution. We will try to find solution with a method. The method is called adomian decomposition. Many of you have already adomian decomposition. Many of you have already maybe used this method, but generally this method is often called the perturbation series method. Basically, you will write a solution as a perturbation series. So we will write this solution also as a perturbation series. In perturbation series, there is a parameter of perturbation. And for us, let us solve this equation, the Oseen flow, which is equivalent to our problem, as a perturbation series, and or this one. This is similar. So this will read this adomian decomposition. So B, the velocity B, which is the solution of the problem, can be expanded as perturbation series, or can be viewed as Taylor series, but who knows, a perturbation series in parameter of gamma. Why? Because if gamma is 0, this equation is going to be 0. So this equation is exactly the equation for Stokes flow. And I've almost forgot to mention the boundary conditions for V, for our two equations, the first and the second one here. The boundary conditions are basically this one. The velocity on R is equal to 0 is 0. There is no moving fluid on the surface of the sphere. And the second condition is that B at R is equal to infinity, is equal to is proportional to Z vector field Z hat times V infinity. These are two boundary conditions, important. So we will decompose our solution in the solution we have found earlier. This is the Stokes flow equation. This is the solution for gamma is equal to 0, and the last term, the second term, will be proportional to gamma. So let's call it Y, the V1 vector field. Again, boundary conditions are the V is equal to 0 on R is equal to A. This is equal to 0 because this is the Stokes solution, so this must be equal to 0. So the condition for V1 is V1 at R is equal to A on the surface of the sphere is 0. We don't bother yet with the solution with the boundary condition at infinity. It will be important later on. So now again, you can write this kind of decomposition for the pressure, the second unknown function. So for the pressure, it's a scalar function. You can write it's going to be pressure, Stokes pressure, plus some additional pressure which we don't know yet. And again, I forgot to mention that this V has associated psi, solution of the problem, and this also we can decompose as V infinity, V0, which is psi 0, and plus gamma of psi 1. Also, this is V0 and this is V1. Oh, this is the curl of this is V1. So these are the equations. Oh, this is the method of adomian decomposition. Now we will substitute this solution, or it's enough to substitute this solution, because you can get the velocity and the pressure from psi alone. So we will substitute F as we have seen in the Stokes video. So we will substitute this equation of this kind of solution in this equation. And clearly, if you do that, if you substitute this solution to this equation, you will arrive at and compare the terms of gamma, you will get this approximate equation. There is psi 0 plus, this is linear, so this is gonna be this with psi 0 plus something with gamma squared because of this, and there is Laplacian of squared of psi 0, which is 0 because it's Stokes flow, plus something of gamma of psi 1, so this will cancel out to get this equation. This equation is the approximate Stokes, approximate Oseen equation, or this is the equation. So this is 0 and this is 1. This is the equation, approximate equation, or the correction to Stokes flow, which we will be solving. And this is much easier. This is very easy to solve. Very easy, but it's really lengthy. Yes, and what next? Let us substitute. We have substituted the solution to here, and now let us focus. Let us remind ourselves what the psi 0 was, and p0 what it is, and v0 we can compute it with this. So firstly, I have to remind you, you can check my video on the Stokes law, but never mind, I will write it right here. What was the solution? The solution for Stokes flow was this. Psi 0 was this in this form. It was rho times r times psi, and rho was r was 1 over v infinity, you can check it, times 1 minus 3 times a over 2r plus a cubed over 2r cubed times this. This is the expression from the last video. And also I didn't mention that this can be simplified, because this is 0, and also its derivative is 0, so that means this is gonna be decomposed in the multiplication of 1 minus a over r squared times something, and it turns out that this is going to be rho v infinity over 2, and there is 1 plus a over 2r times 1 minus this is not necessary to know, but you can always multiply it out and show that this is basically the same. For the pressure, it's much more easier. The pressure term is easier. The pressure term, it was, again, you can remember the pressure term was 3 times v infinity times eta a over 2 times r cubed. I think it was this, but I'm not sure of that. But we will not use it. We will not use it either. So this is the equation for pressure, and there should be a minus sign. Yes, this is the equation for the pressure 0. So next we will basically compute, because we need to compute this Laplacian of psi 0. We have to compute this Laplacian, before. So what to do? It's really not hard to do. It's really not. But we have to look at my video earlier. There is the relation. I think that's the best. The solution for this letter phi, which was defined as Laplacian of phi 0, you can check it, and this was basically the Laplacian was I forgot to mention there is also z. This is the expression for the pressure, and this is 3 this is 3/2 v infinity times a times rho over r cubed. You can use basically this formula to compute this expression from this. It's very easy to do, but I will save much time with that. So this is the equation for psi 0, and there also I have to mention that we will need in the computation this kind of expression. It's r prime over r, and you can compute it very easily, and this is gonna be 3v infinity a over 4r cubed 1 minus a squared over r squared. This is the expression of the derivative with respect to r over r. This is the expression, so you can check it yourself. We will need it, so I have to write it here. So next, now we will substitute this form in this equation. So the Laplacian of the square of Laplacian of psi 1, it's gonna be z hat dot product with gradient of Laplacian of psi 0, and Laplacian of psi 0 I will compute very easily, because Laplacian of psi 0 it's going to be this. Laplacian of psi 0, it's a Laplacian of this Laplacian. Oh, this is the Laplacian of psi 0, so I have to compute the gradient. The gradient times the z hat. So this is z hat times the gradient of this, which is 3 v infinity a rho over r cubed times phi, and this is what? There's going to be derivative with respect to rho, but it will cancel out with this dot product, and this also is 0 because it's proportional to phi. Again, dot product with z is 0, so the only term which will survive is minus 3 over r fourth, the dot product with this, so it's z over r, so it's to the 5th power times z, so it is going to be minus 9/2 v infinity a times z times rho over r to the 5th power times phi hat, and this is the equation for we will solve. Let us first, before we do that, focus on the boundary conditions. Basically, there are two boundary conditions. Let us consider the boundary conditions. But firstly, we have to solve this. So we will solve this by this substitution. We can already guess the solution because this Laplacian squared is proportional somehow, this Laplacian is proportional to z rho times some function of r. So, as you have seen, if we take Laplacian of 0 times something proportional to s, it will stay the same. It will stay the same form. So we can guess the solution already. We can guess the solution, and we will guess this solution. Psi1 we will guess as this. It's as we did with the Stokes formula: z times rho times s times psi hat. This is our guess, and the boundary conditions have to be satisfied. The first boundary condition, it's the velocity is equal to 0 at r is equal to a. Again, velocity is curl of this, and the curl takes the derivative. Yes, it's really trivial thing to think about, and the derivative will be here, 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 and here. This will vanish immediately when s and s prime will vanish at r is equal to a. Why? Because there is no second derivative of s, so this is proportional. The curl of this is proportional to s and s prime, so this will vanish at r is equal to a when s and s prime is equal to 0 at a. So the condition will be, s at a is equal to 0 and s prime at a is equal to also 0. Again, the condition, there is a second condition I have not mentioned, but basically this cannot blow up. This term cannot be bigger than this. This cannot blow up at infinity. So the v1 can be at least the constant of order, the constant. So, but when s is the function of r, this is function of r squared. If we take the derivative, this is going to be a function of r alone. So s has to be at least a function of 1 over r and more power. So 1 over r squared and 1 over r cubed, whatever. But not a function of a constant, because otherwise it will blow up. Not function of r squared, etc. So s can be a function of 1 over r, but not a function of constant. So it's r 1 over r squared, etc. It's a simple condition. Next, we will substitute in this solution into this Laplacian. It will be really easy, very, very easy, because now you have the formulas. So these are the formulas. If you substitute in this solution into the first Laplacian, it will be this. So it's gonna be Laplacian of this, which is Laplacian this minus 9 halves, etc. minus 9 halves v infinity a times 0 over r to the 5th power phi hat should be the second Laplacian of phi, which is Laplacian of z rho s phi, and which is Laplacian of z rho, and this is s double prime plus 6s prime over r times phi. We have seen this equation already, and this is going to be, if we denote this part with the letter t, as we did with r and q in previous session on the Stokes law, it will be the same, exactly the same. So, but with t, the second derivative 6t prime over r phi hat. This is and this should be equal to minus 9 over 2 v infinity a z blah blah blah. So that means that t must be minus 2 minus 9 halves v infinity a times 1 over r to the 5th power is equal to t double prime plus 6t prime over r. This is the equation, the differential equation. This differential equation is very easy to solve, and I left it to the left it for the reader, and now I will write the solution. The solution is 3 v infinity. You can guess already the solution is very easy to do. It's going to be some power of r, and this power is r could be minus 3 power, so it's 1 over r cubed plus some constant h plus some constant g over r to the 5th power. Why? Because as you see, this is Euler equation. The characteristic polynomial is lambda squared minus plus 5 lambda, because it is 6 lambda. So the solution is 0 and minus 5 for lambda, so it's r to the 0th power, which is constant, and r to the 5th power. And you can guess the solution for this. It's some constant times 1 over r cubed, because the second derivative will get this, and this is basically the solution. Also for the same also for s, because this is t, and this should be equal to this part. So s is going to be this, and it is also a differential equation, and when you solve it, this is also the second power more, so it's something over r, and if you solve it properly, that you will get that s is equal to again, this solution will remain, because the solution, the equation is the same. This is the homogeneous solution, will be the same, so it's some constant a plus b over r cubed, but the particular solution is minus 3 infinity v infinity a over 16r, that's the particular solution, plus some constant of r squared plus b over r cubed plus c plus d over r to the 5th power. These solutions are from here, or the homogeneous solution to this there, these are the same. As we've mentioned, s cannot be a function of r, so this should be 0, otherwise the pressure will blow out and everything will blow up. So this cannot be also, because it's r squared. So this is only these. Oh, there are only two constants, b and d. Oh, we are very lucky. We are very lucky, because if we have just two constants, then the solution is very easy to find, because the conditions are s at a is 0, s at prime at a is 0, so we have to solve these conditions will lead us to solving the system of equation. If we differentiate it and substitute a, and substitute also in not yet differentiated s, you will get this. It's this minus 3 in v infinity over 16 plus b over a cubed plus d over a to the 5th power is 0, and minus 3 plus 3 v infinity over 16 a minus 3b over a to the 4th power minus 5d over a to the 5th power is 0. You can solve it. It's very easy to solve the system of linear equations. The solution is this. I will write it here. It's very easy. It's 3/8 times v infinity a cubed for b, and for d it's minus 3 over 16 v infinity times a to the 5th power. So we now have s as a function of r and other stuff, and if we substitute in this, you will get the expression for s, and again, as in case in Stokes, you can put it in one bracket and simplify it a bit, and you will arrive at this. So the solution for psi1 vector field is therefore, we have assumed this kind of solution, 0 as phi, and this solution is therefore is therefore 0. Yes, it can be simplified, but I will write it down. It's minus 0 times 3v infinity a over 16 r times minus 1 minus 2a squared over r squared plus I to the 4th power over r to the 4th power. And again, it can be simplified because minus 0, this is the result of simplification, 3/16 r, and there is 1 minus a squared over r squared, the whole squared, and phi. This is the solution for the psi. And again, you can compute its Laplacian. It will turn out to be very useful Laplacian of psi 1, which by definition, or you can look here, Laplacian of phi 1 was 0t. So it is also, we are also getting information about t function. Oh, I forgot the phi here, t, and it's going to be, you can differentiate it. This is going to be vanishing because this is 1, and yes, it's oh, this is not, this is going to be vanishing because it's 1 over r 5th power, yes. So you will arrive at the simple expression, and the expression is 3v infinity a over 4r cubed times 1 minus 3a squared over r squared times, oh, I almost forgot 0 and phi hat, and this is 0 t. T is basically this function. Well, then I have to switch my paper. Now for the pressure. For the pressure, it's very easy because we can also derive the equation for the pressure, and we already know the Stokes equation was, if we the Oseen equation was minus there is gamma of times z hat times Laplace, there is a gradient of v plus is equal to minus 1 over eta gradient of pressure eta times Laplacian of v. This is the equation of the Oseen flow, and if you substitute in, v is equal to v0 plus gamma v1, and p is equal to p0 plus gamma p1, you will get the equation for the pressure 1 we are trying to find if we compare the gamma coefficients. And the equation is this. It's the equation for v. Basically, we have maybe we have seen it, but I'm not sure if I've write it before. It's z dot product with Laplace gradient of p0, and this is equal to minus 1 over eta gradient of p1 plus Laplacian of v. This equation is the same as we've solved in a few minutes before, because if you take the curl of this is z times Laplacian of psi 0, and there is double Laplacian of Laplacian square of psi 1. So this is the equation in the different form. And from this, it's easy to write that 1 over eta gradient of pressure, it's equal to pressure 1, the first correction, Laplacian of v1 minus z hat dot product with gradient of v0. So again, this is scalar operator, and this is also scalar, so you can change it with curl operator, which is in here and here, because v0 by definition is curl of psi 0 and v1 is by definition curl of psi 1. So this is gonna be curl of, and there is psi Laplacian of psi 1 minus z dot this times psi 0. Oh, it's very easy to, oh, psi 0 vector field. This is very easy to justify, it's really easy. Now you have to compute this to get the information about the pressure. So I will compute this. It's very easy to compute that. So I will do like this: the Laplacian of psi 1 minus z hat dot product with gradient of psi 0. Well, we know that this is Laplacian of psi is rho s 0 times s phi vector minus z dot product with gradient rho r phi vector phi hat. And this is very easy because this is z rho t. Again, we are using our formula minus, and also this here. Look, this is very easy to, because this is going to vanish. Again, this argument holds the same. This is going to vanish. So only term which will survive is derivative of r prime times r hat, and r hat dot z is z hat is z over r. So this is gonna be z from this dot product rho and r prime over r times phi. So we have to compute t minus r prime over r. Well, I've mentioned that this is going to be important later on. Oh, this is the time for using the formula for r prime. You can use this is for r prime over r, and I think I've put it right here. This is the formula for r prime over r, and you also know the Laplacian for psi 1, which is here. So you can substitute in and subtract these together, subtract these, and you will get this expression. So 1 over eta gradient of p1, it's curl of z rho t minus r prime over r phi, and this is going to be the curl of, and this is so easy, it's z rho, and if we substitute in, you will get exactly this. It's minus 0 times 3v infinity a to the ra cubed over 2 times r to the 5th power times phi hat. Yes, it's really neat. And you can also say it's a curl of this form is familiar to us. It's some z rho times some function of r, let's call it p, and phi hat. And this can be computed very easily. This is going to be, if you take the curl of this, you will get this is z hat, and curl with this, it's a minus. Again, you can use this table. Z hat curl of phi is minus rho, so it's minus rho times p, and the second term is rho hat vector product with cross phi. Rho hat phi is plus z, so it's plus z p, the function, and there is P with respect to R, so it's going to be Z rho derivative of P times R hat, and R hat cross phi is minus theta hat. So this is minus theta hat. So this will be, and the last term is the curl of phi hat vector, which is 1 over rho times z, so it's plus z p and z vector. So it will be the same as this. So you can write the 2 here and don't bother with this term. So this is the same term. Now, as you know, the gradient of P can be written in this form. 1 over eta is gradient of P is P1 with respect to R times R hat plus P with respect to P1 with respect to theta times gradient of theta, which is 1 over R theta hat, as you know from this expression. So this is going to be this, and this should be this expression. So if this is true, that it's true for every component. So let us focus on R component only, and this should be an R component of this. You can get this by taking the dot product with R hat. So this should be if you take dot product with this equation and this, you will get the component only. So this is not R hat, so we will get the R hat times rho hat is rho over R. So this is gonna be minus rho squared over R. Rho squared over R, yes, times P plus, there is plus 2Z squared over R times P, and this is minus 0 because rho hat dot this is 0, so this is the expression for this. So now you have to integrate it with respect to R when theta is considered constant. So for that purpose, I will, for the moment, write rho as a function of R and theta, and z as a function of R and theta. So it is gonna be this. It's P times R times, there is minus sine squared theta, yes, that's it, plus 2 times cosine squared of theta. These are the 2, and there is, yes, it's correct. Now if you integrate it, you will get the pressure plus some function of theta. But this function is 0 because there is no dependence on phi at r is equal to infinity, so you can integrate it freely, and there is no constant pressure because, yes, the pressure is 0 at infinity. Oh, I forgot to mention there is another boundary condition. So pressure at infinity is 0, so there is no constant either. Not depending on phi either, so there is 0. So you have to integrate it just this P, and you've seen what P actually is. P is over there. It's minus 3 blah blah blah, and if you integrate it, it's R times R is R to the 4th power, so it's minus will cancel, so it's 3 will cancel, so it's 1 over 2 times v infinity a cubed over R cubed. So the pressure is then v infinity a cubed eta over 2 times r cubed times this. But again, I will write r to the 5th power and multiply this by r cubed. So this will become r squared. So this will become minus rho again plus z 2 times z squared. This is the expression for the pressure one, the first correction in adomian correction. And there is no term for there should be a term for p infinity, but I said that it was 0, but you can let it here, but it's 0. It doesn't matter, it does not add to anything. Now we will compute the contribution to the Stokes correction for the Oseen. This pressure alone and the phi 1 vector field will produce these beautiful pictures of the flow and circulating toroidal vertices. But not yet quite, but I will show you why. There is a little problem with this solution alone, with pressure is equal to P0 plus gamma times this and psi. So now contribution to drag force. We will compute the drag force as I've promised in the name of the video. Contribution to the drag force. So it's funny contribution. Why? Because it's 0 from this alone. But why? Well, we'll see why. If you take some portion of the sphere and there is a little surface, again as in Stokes video, there is little normal. No, there is normal, and there is force with respect to this normal surface. This little surface has the area of ds. Then the force, by definition of the stress tensor, is going to be n hat dot product with T force. So stress tensor. The stress tensor. But from the symmetry we know that we only have to know the z component of this force. So it's now not if the arrow is missing now, so it's going to be n dot the stress tensor dot z hat, and for us n hat is r hat because we are dealing with the sphere. With a sphere. So now the force then can be computed. The force of drag can be now computed as the double integral of this t zn times ds, and as you know, this is not depending on phi vectors, so it's gonna be 2 times pi. The Jacobian has a squared in it, so it's 2 times pi times I squared times integral of from 0 to pi times this expression. So this is r hat, the stress tensor times z times d theta. Oh, I'm sorry, I forgot the Jacobian term, which is sine of theta times d theta. This is the expression for the force. We can split it into 2 parts. The first part from the pressure, which will turn out to be 0, it's going to be 2 pi a squared and integral from 0 to pi times this, and we already know the pressure. This is for our purpose. The first term is is proportional to the pressure P minus Pi minus the pressure times I. So this is minus P d sine theta d theta. Now we know that pi is a function. This should be computed at r is equal to a. The pressure is function of sine squared and cosine squared. And if you do the multiplication, there will be sine. Oh, I'm sorry. I forgot cosine term, because r dot z is 0. R dot z is cosine of theta. If you can see, this term multiplied with this is sine cubed, and this is cosine, and sine cubed looks like this, and cosine looks like this. So this is going to be 0 from the integral because of the symmetry, and this is the second term will go like cosine cubed, which is this, times sine, which is this. So there, and again it will vanish because this, the cosine is squared, this looks like this, times sine, it will look like this, or some kind of bumpy function. And again, cosine is anti-symmetrical with respect to this, so this is also going to be 0, so it is 0 from the integral. And for the velocity term, viscous term, you have to compute this stress tensor. Its proportion is eta times this plus gradient of V transposed at r is equal to a. As you know, B gradient of V is gonna be what? It's gradient of curl of psi, and gradient of curl of psi, it's because we know psi 1. Oh yes, I have to compute this term, and there is also gamma, but it's 0 because the stress tensor is gamma factor. It's like from the decomposition, because V is V0 plus gamma V1, and there is gamma V1. So it's this is gonna be 0 s times s times phi hat, and this is the second derivative. And if the second derivative will not act on s, it will vanish. Why? Because s and s prime will vanish at r is equal to r is equal to a. So you can take curl of this and then apply gradient only on this term. So this is the simplification. I was not aware of it before in the last video on the Stokes flow, but now I am. So it will be much more easier for us. So this is the gradient of z rho times s prime times r hat cross phi hat, which is r hat phi hat is minus theta, so it's minus theta, and the gradient of this is going to be gradient of this, because rs is at r is equal to a, yes, is going to be, we have to take gradient of not this because it's complicated. Oh, that's not the reason, because it will vanish. So we have to know only the gradient of this term, because otherwise it would vanish. So it's minus 0 s double prime times r hat theta hat. And as you can see, the only term which will survive in this dot product is this first term, because the transpose will switch the order of this, but r is perpendicular to theta. So the only term will be r dot. The only term from the force will be 2 pi with minus 2 pi a squared eta integral from 0 to pi. There should be minus sign, because z hat dot theta hat is minus sine theta, so there should be plus instead. So it's s double prime, and there is z rho, which gives us a squared cosine theta and sine theta, and there is another sign from the dot product, and there is another sign from the Jacobian, so it's sine cubed. So it's this is positive on and symmetrical on 0 to pi, and this is also this antisymmetrical, so it will cancel out because this is a function of r. Just a is a constant when r is equal to a, so this is 0. So there is no contribution, which is really odd, I think. Or not? It's odd because we forget something. This something is very important thing, which I've not. Where is the missing force? That's the question. Where is the missing force? Where is the missing force? Because there should be an additional drag force term. But where it is? Where it is? Well, we found a particular solution to this equation: z hat time dot product gradient of Laplacian of psi 0 is equal to Laplacian squared times psi 1. We found psi 1 as our solution to the problem, to this problem. But there is another solution, because as you know, if you add to this solution, well, say if you change phi 1 with phi 1 we have found plus another solution, and say that this is 0, then this solution will also satisfy our equation. So that's the trick. This solution will also, because this is a homogeneous, we can add this really simple principle. We are just adding a homogeneous solution. But there is another catch, because this homogeneous solution has to satisfy all boundary conditions. If we substitute, we can guess the solution in this form. It's something like this. This is another r prime. So this is one form of the solution, because this is the Stokes. This is the Stokes type solution. I would tell you. Well, but there is another catch, because if you substitute in, you will get a differential equation of fourth order. So there should be 4 constants left to determine, but one of them should be 0, because otherwise it will blow up, as you have seen already in the Stokes solution at infinity. But it also have to satisfy conditions at that v or v2 or for this purpose is 0 at r is equal to a. So this will erase another 2 constants, because r prime and r should be 0 at a. So there is just one constant left. So that means that psi 2 is directly proportional with some constant a to the solution, to the Stokes solution. This is interesting relation. So the overall solution is not just phi 0 plus gamma phi 1, but is this. It's the overall solution. I will write here is then is then phi is phi 0 plus gamma of phi 1 plus phi 0. This is the solution of the times a. We don't know yet the constant a, and you can regroup it like this. This is psi 0 1 plus a gamma plus gamma of phi 1 if you want. From this clearly you can see, because of the equations are linear, so then the force, the direct force, must be the Stokes force, which is 6 pi v infinity eta a, but there is another 1 plus a gamma, and we are almost there, because Oseen correction tells us that direct force is 6 pi blah 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 times 1 plus, and there should be the missing 3/8 times Reynolds number, which we will find very easily by this principle. Oh, this is the time where the magic begins. So I would be grateful when anyone finds a reason why this is correct, this assumption I'm making, or if anyone will find appropriate justification or another solution for this justification. Imagine you have the Oseen flow. There is some vertex, there is another one symmetrical to one, and this is the these are the streamlines. In Oseen approximation, you will consider a small amount of inertia of the fluid. So the fluid is going in this direction. There it changes its momentum, and there also changes its momentum. So in this direction, the overall change in momentum will cause the fluid at far away on the equator to be proportional to gamma. This is interesting thing, but on the other hand, if we focus on this stream of water or the fluid, overall the overall change in momentum should cancel out, so there should be no change in velocity. So I think that is my assumption, that at v infinity the velocity should be v infinity times z hat, but there can be a term proportional to gamma, but my assumption is that this term is 0. There is no proportionality to gamma, or it can be proportional to gamma squared, but it's second order decomposition. So this is my assumption, that it's proportional just only to this. So this is the assumption, but it is only when theta is equal to 0 in this direction, or this, it's the same, this direction. So the velocity should be v infinity z hat, and there is no term. How can we achieve this? Well, you know that v is from this, the correspondence is really obvious. It's v0 times 1 plus a gamma plus gamma v1, and this must hold when theta is 0, r is infinite. And this from this we know that v0 is the curl of psi 0. So this is psi 0, which is rho r phi plus gamma of this, which is z as rho as phi hat, which is exactly y1. This is the forms of the solution, and this is, and if you compute the curl, it's very easy to do. It's 1 plus a gamma, and we have done it before, in the case of P, but with Z. So there is no this term. There is no this term. So it's this without. Oh, there is no this term. So it is this without Z, because the term from Z, and the other is 0 S phi hat, which is exactly this form. This form of the curl. So it will be this. From this we have this solution, this curl, which we have considered earlier in the Stokes video, I think. Also, so this is this. It's 2 times Z. This is the same as in the row I've shown you a few seconds ago. This is this row hat. This is S prime. Oh, this is not S prime. This is just S. Well, at theta is equal to 0, there are some terms which will cancel out, and these terms are this, because this is perpendicular to R at theta 0, and this is also 0. This is 0 also. So V is then 2R plus gamma times 2A R, if we do some simplifications, times S, and we are substituting in, because at theta is equal to 0, R is equal to Z, or R is equal to Z, so these are the same, times Z hat. So it means that this will automatically at R is equal to infinity. This is V infinity by definition of R, because this is the Stokes solution. This should have be V infinity, and there is also V infinity if we take the limit. But the condition I've mentioned, that this term should be 0 order of gamma, means that A is equal to the limit to the S divided by V infinity, so with minus. So A should be the limit at as R is going to be infinity, times minus Z or minus R, it doesn't matter because R is Z when theta is 0, times S times 2 divided by V infinity. And as you know, this is limit as R is going to be infinity. This is minus 2Z, which I'm going to write R instead of. So it's minus 2R over V infinity. S, it was minus 3, you can look it up, minus 3 over 16 times minus 3 over 16 times V infinity times A divided by R, and which is basically the the S function. Yes, 1 minus A squared over R squared. And if you take the limit, minus this, and this should be 8, and there is R V infinity. So it is going to be A is equal to 3/8 times A. So it's 3/8 times A. Well, then from this you can immediately write the expression for the drag force, because the drag force was 6 pi eta V infinity A times 1 plus A times gamma, and A times gamma is 3/8 times A times gamma, and as we know, the gamma was rho of the density of the fluid, not this is rho, but rho density of the fluid times the velocity of the fluid at infinity divided by eta, and this is the Reynolds number defined earlier, so this should be dimensionless Reynolds number. So this is 3/8 times the Reynolds number. So the solution for the drag force is then the drag force formula, the Oseen approximation. It's 6 pi eta v infinity a times 1 plus 3/8 times the Reynolds number, and this is the famous equation of Oseen, which I think you have to remember, but maybe it's not so famous, but I don't know. For me, it's really amazing, this formula. Again, if you want, you can compute another approximation. There is another term, and there should be, I don't know, 9/20 from the Navier-Stokes equations. One can derive that the next term is of order Reynolds number squared times the logarithm of Reynolds number, which has been done in the recent years by, I don't know who did it, but I will definitely write it under in the video description. Also, for the bonus, there is a bonus for this video, because you can also because you know now that v is equal to v0 times 1 plus 3/8 of Reynolds number plus v1, which you can compute from the curl of psi1, and then you can compute, or you can render this particular this picture from the vertices. And if you have a time, you can derive the separation point of the flow, or the length of the tail, which is going to be this equation is the equation of the length of the tail. You can find, for example, the separation angle where the fluid is separated from the surface of the sphere, and change its direction, or it's separated. This is separated from the ear. And you can also compute the critical value of Reynolds number when this picture happens to or arrive to reality, because otherwise there is no vertices. You can also find the coordinates of this like a torus, this vertex torus. You can find it also. It's not so hard, but there should be done some numerical analysis. It's really not so hard. The second thing I can tell you is that from this expression you can compute the drag coefficient, because Newton tells us that the drag force is equal to 1/2 times the density of the fluid times v infinity squared times the area of cross section of the body times the coefficient of drag. From this coefficient of drag is, if you substitute in for the force which is here, you will get this expression for the drag, 12 divided by the Reynolds number times 1 plus 3/8 times the Reynolds number, when the density and the velocities are high enough, the Reynolds number is big, this should tend to, if you take the limit as Reynolds number goes to infinity, this should tend to 9/2, which is 4.5. This is a very bad result, because as you know, maybe the Dirac coefficient of the sphere is actually not 0.33. So this is quite a difference, I should mention. Finally, I will draw a picture. What we know, or what we know now. What we know now when computing the Dirac coefficients of the sphere. Let's say that this is the axis of the Reynolds number, but in the logarithmic scale, so Reynolds number is 10 times 10 to the power of x, and this is x, so this is 0 or -5, I don't know. Oh, minus blah blah, there is 0, there is 5 and 10 and something like this. And if you do the analysis, the Dirac coefficient, the plot looks like this. So this is the plot of Dirac coefficient. I don't know whether the numbers are correct, but this is how the graph looks like. And also this is the Stokes approximation, which is in here. This is the Stokes approximation. And if you add Oseen approximation, it will look like this. It will look like this. And this is 9/2, and this, oh, it's not so proportional, but this is 0.33. This is the Newton's equation for high Reynolds numbers. I don't know whether there is exactly 5 or not, but this is the picture how the Dirac coefficients look like. Yes, it's not a big change in the Dirac formula, but definitely it's better than the Stokes law. So that's it. I hope you enjoyed this video. Oh well, and maybe next time in this section I've derived the equation of the Dirac for Stokes of the Oseen flow. I should have write it right there, but never mind. 6 pi eta 1 plus 3/8 Reynolds number. This is the equation. This is how it looks like when the Reynolds number is greater than critical Reynolds number, which is 8/5. And again, this is the derivation. You can tell me if you have questions. I will be really grateful to read your questions in the comment in the next paper. The next paper is this, and finally we have arrived to this particle equation, 6 pi eta v infinity times a. So I hope you've enjoyed that, and see you next time.